Hi everyone, I hope that you did well on your quiz that you just got finished taking. I'm going to talk to you now a little bit about some techniques of differentiation. This is very exciting stuff and I will try to contain my excitement, although I don't love being on the video, so I think I'll be okay. I do want to remind you a couple of little things about notation that we talked about with derivative. So when we talked about the definition of a derivative, we really used the notation f prime of x, and we had the definition. The limit as h approaches 0, f of x plus h minus f of x all over h. Okay? But we also talked about other things that we use to notate a derivative. One of those was if we have a function like y equals, I'm just going to make one up really quickly, 2x squared plus 9, we can say that the derivative of that, or dy dx, is, and then what we would use here is we would say d dx of 2x squared plus 9. So we're really basically substituting 2x squared plus 9 in place of the y on this side. And you're going to see some notation like this quite a bit today. So I just want you to be aware what we're looking at. Okay? All right, we have several theorems to talk about that help us define our techniques of differentiation. And so we're going to jump right in with the first one, theorem, which says the derivative of a constant is 0. Okay? The derivative of a constant is 0. So the way we would write that in notation, we would say d dx of c standing for constant, equals 0. Okay? When you think about it, it sort of makes sense, because if we have some sort of function, f of x equals 2, for instance, and we want to, if we were to graph that function, here's x, this is f of x, we know that, or hopefully we know, that that would be a horizontal line at 2. Well, remember, when we find the derivative, we're talking about the slope of a line that's tangent to it. So what would the slope of any tangent line along this one be? It would always be 0, because the slope of this line itself is 0. Okay? So that kind of makes sense when we think about it. But let's just make sure that we're clear and do a few examples. So the derivative of something like 2 is 0. Okay, that's pretty straightforward. The derivative of a negative number, negative 14, is also 0. How about the derivative of an irrational number like the square root of 5? The square root of 5 is still a constant, so its derivative is also 0. Finally, we can talk about the derivative of something like pi. Remember, pi is really a constant, so its derivative is also 0. Okay? All right, so that's a pretty easy one. That one's pretty straightforward. Let's move into some that are a little bit more complicated. The first one is going to be called the power rule. Power rule. And it starts out saying if n is a positive integer, if n is a positive integer, then d dx of x to the nth power is n times x to the n minus 1. So really what happens here with the power rule is that the exponent comes out front as a coefficient, and then you take the exponent down by 1, okay, on the variable. So let's look at a couple of examples of that. So if I want the derivative of x squared, the power rule says we're going to take this exponent and we're going to move it out front as a coefficient. It's going to be 2 times x to the 2 minus 1 power, or 2 times x to the first power, or just 2x. So the derivative of x squared is 2x. Okay. How about the derivative of x to the 12th power. Okay. The derivative of x to the 12th power, again, using the power rule, says we're going to take the exponent, we're going to bring it out front as a coefficient, and we're going to have x to the 12 minus 1, or we're going to take that down by 1 and call that 12x to the 11th power. Okay. Pretty straightforward, right? Okay. So let's move on, and we have another theorem that is an extended power rule. Okay, the extended power rule, which says if n is any integer. Okay, so now we're not just saying a positive integer or positive exponent, but if n is any integer, then the same thing applies. D dx of x to the nth is n times x to the n minus 1. Okay? Now, let's see how this changes things a little bit. That means if I want to do, or if I want to know the derivative, if I want to know the derivative of x to the negative 9th power, okay, again, we're going to bring that exponent out front as a coefficient, so it's going to be negative 9 x to the, and we have to do negative 9 minus 1. Now, be careful because this is where it can get a little bit tricky. Negative 9 minus 1 is negative 10. So we end up with our derivative of x to the negative 9 is negative 9x to the negative 10. Okay. Now this comes in really handy when we can use the power rule to help us find the derivative of things like 1 over x. Okay. If I want to find the derivative of 1 over x, I'm actually going to think about rewriting that as x to the negative 1st power. Because I can do that with that and get rid of the fraction so that it's not in the denominator anymore. This power rule, notice, only works when we've got things not in a denominator. So that's why we're going to use this negative exponent. So the negative 1 is going to come out front as a coefficient. We're going to have x to the negative 1 minus 1, which is negative 1 x to the negative 2 power, or we would probably even rewrite our answer as negative 1 over x squared. Since our problem began with x in a fraction in the denominator, we will go ahead and rewrite this in the same fashion. So it's negative 1 over x to the 2nd. Okay? Now, notice that this is only talking about integers, okay, in both cases. And integers we know are positive and negative whole numbers and 0. But this actually also works for other types of exponents. So let's do something first that we haven't done yet. So we're going to use the definition of the derivative. To find the derivative of the square root of x. Okay, so we're going to start by using the definition of the derivative to find the derivative of the square root of x, and then we're going to show that this extended power rule actually works for some exponents that are not integers, but that are actually fractions. All right, so dy dx is going to be the limits as h approaches 0 of the square root of x plus h minus the square root of x all over h. Now I'm going to kind of quickly go through this just so you can see. You can pause the video later and see what's happening. Again, I can't do anything here to simplify to be able to cancel out the h on the bottom, so I'm going to need to rationalize the numerator. And in doing that, I'm going to multiply by the square root of x plus h plus the square root of x over the square root of x plus h plus the square root of x. Now, when I do that on the top, I'm going to be left with x plus h minus x, the difference of two squares, and then I'm going to have h times the square root of x plus h plus the square root of x. Okay. Well, these x's are going to cancel, so I have the limit as x approaches h. And also these h's now are also canceling, so I'm going to end up with 1 over the square root of x plus h plus the square root of x. Now I am ready to find the limit as h approaches 0, so I'm going to have 1 over the square root of x plus 0 plus the square root of x, or 1 over 2 square roots of x. And that is our derivative of the square root of x. Okay? So pause the video now if you need to go back and kind of work through some of that yourself and see what's going on. Okay? I'm going to try to use a different marker now because that one's running out. Now, we said that the power rule might also be extended then to account for or to apply to exponents that are not integers but that are, in this case, rational. So let's think, let's look here, find d dx square root of x. Okay? So the derivative with respect to x of the square root of x is really the same as taking the derivative with respect to x of x to the 1/2 power. Okay? Now, according to the power rule, what we need to do is take this exponent and put it in front as a coefficient, so 1/2 times x to the 1/2 minus 1. Well, 1/2 minus 1 is negative 1/2. Okay? And remember, this little negative exponent is saying, move me. So we're going to move that to the bottom. So we're really going to have 1/2, and then this is 1 over x to the 1/2 power. Oh, well, I can put all that together and call that 1 over 2 square roots of x. And we notice that using the power rule or using the definition of the derivative gave us both the same answer in those cases. Okay? So that power rule can actually be used quite a bit. All right? Very, very nice. In fact, there's a song about it. Would you guys like to hear it? I have to find it on the computer. Hang on. Real fast. Here it comes.
When you have a times an x to the b, you know you always use power rule. Look, abx to the b minus 1. Here's the derivative. Power rule. Derivatives of constants are always a slope of 0. Square root is the 1/2 power. You have nothing to fear. Oh, how can you lose? For all polynomials, you can't forget all your troubles, because everyone knows you use power rule. 1 over x is just power rule. X to the minus 1, power rule. For polynomials.
Okay, we'll listen to the rest of that song another day. All right, we're going to move on and continue looking at more theorems for derivatives. So the next one is called the constant multiple rule. Now, we did talk the other day about, remember when we were talking about limits, that we can always take a constant and move it through a limit. And keep in mind that anytime we're taking the derivative, it's really just a limit. So we can also do the same thing with constants when we are taking derivatives. So it says if f is differentiable at x and c is any real number, times f is also differentiable at x, and dx of c times f of x is the same as c times dx of f of x. Okay, and we're going to look at a couple of examples of how the constant multiple rule helps us out in finding derivatives. Okay. And we're getting close to being done. Okay, so the first example we're going to do is dx of 4x to the 8th. Now, what's going to happen is that a lot of you guys are going to notice pretty quickly what the shortcut is here without having to write all of these steps out, but I'm just going to show them all again just so we'll make sure that we're using the constant multiple rule and the power rule every time. So since we're taking the derivative of something 4 times some other function, in this case x to the 8th, we can say that that's really the same thing as 4 times the derivative of x to the 8th. Well, we all now know that the derivative of x to the 8th using the power rule is 8 times x to the 8 minus 1, or x to the 7. And we can simplify this by then just calling this 32 x to the 7th. Okay, pretty straightforward. Let's look at another one. Let's find the derivative of negative x to the 12th. Now, I think we already looked at one that was x to the 12th, the derivative of x to the 12th, but this one's negative x to the 12th. And keep in mind that that negative there is really like a negative 1. So we can really have negative 1 times the derivative of x to the 12th. Well, the derivative of x to the 12th is 12 x to the 11th. Okay, again, brought the exponent out as a coefficient, took the exponent down by 1 to 11, and so we end up with negative 12 x to the 11th. Okay. All right, one more of these. We're going to take the derivative of pi over x. Okay, pi over x. Now, keep in mind that pi is a constant. Okay, we talked about earlier that the derivative of a constant is 0, but we're not taking the derivative of just a constant in this case. We're taking the derivative of a constant times a function. So we're going to actually move the constant out. So we're going to call that pi times the derivative of 1 over x. Well, we just talked about how we can find the derivative of 1 over x using the power rule. We're actually going to call that the derivative of x to the negative first. And we know that the derivative of x to the negative first is negative 1 times x to the negative 1 minus 1, or negative 2. Or we end up with, in this case, negative pi over x squared. Okay. Now, I do also want to remind you about your notation when you're doing this. So you'll notice that I'm writing d dx, d dx, d dx. At the point that I actually take the derivative, I no longer write d dx. Okay? So also be very cautious about your notation. Okay? All right, we have one more little thing to talk about. It's not too bad. And again, it kind of goes back to what we talked about when we were doing limits, when we said that the limit of a sum was the sum of the limits, and the limit of a difference was the difference of the limits. And again, derivatives, really keep in mind, are limits themselves. And so the same thing applies when we're talking about derivatives. However, be careful, because while we had a rule that said the limit of a product was the product of the limits, that is not the case for derivatives. And we're not going to talk about products and quotients today. We're going to talk about those another day. Okay? So this is only going to apply for sums and differences. All right, so this one is the sum and difference rules. If f and g are differentiable at x, then f plus g and f minus g are differentiable at x, and d dx f of x plus g of x is equal to the derivative of f of x plus the derivative of g of x. I'm going to have to change markers again. So give me a second. And f of x, the derivative of f of x minus g of x is the derivative of f of x minus the derivative of g of x. Okay, so get those written down. I'm going to grab another marker really fast. Okay, we're going to try green. So let's look at a couple of examples of how this works. And this is where it really feels like we're taking the derivative now of polynomials, because we're going to have several things added or subtracted together and be able to take the derivative. Ooh, I hope you guys can see this okay. So we're going to talk about the derivative of 2x to the 6th plus x to the negative 9th. Okay? Now, even though that might just feel like a regular old, well, not really a polynomial, but it is polynomial in nature, this is really just like the derivative of 2x to the 6th plus the derivative of x to the negative 9th. Well, this has a constant in front of it, so I can actually say that that's 2 times the derivative of x to the 6th. And this one does not, so I'm going to leave that alone for a minute. And now we're going to apply the power rule to all of these things. So we'll have 2 times the derivative of x to the 6th is 6x to the 5th. And the derivative of x to the 9th is negative 9, x to the negative 10. Keep in mind, it's a negative 9 minus 1. Okay? So we're actually going to have 12x to the 5th minus 9x to the negative 10. And that's our answer. Okay? Okay, let's look at one more. This can actually be extended to be any number of terms, even though the actual theorem only shows 2 terms or 2 functions being added or subtracted. It can actually be extended to being any number of them. So, here we go. Example. Find dy dx if y equals 3x to the 8th minus 2x to the 5th plus 6x plus 1. Okay. So dy dx is going to be d dx of 3x to the 8th minus 2x to the 5th plus 6x plus 1. Or, again, these are all individual polynomials that have been added or subtracted, so we could actually break that up to be the derivative of 3x to the 8th minus the derivative of 2x to the 5th plus the derivative of 6x plus plus the derivative of 1. Well, again, whenever we have a constant multiple, we can always bring that constant out. So this is 3 times the derivative of x to the 8th minus 2 times the derivative of x to the 5th plus 6 times the derivative of x, interesting, plus the derivative still of 1. Okay. All right, so we're going to have 3 times the derivative of x to the 8th, which is 8x to the 7th, minus 2 times the derivative of x to the 5th, which is 5x to the 4th, plus 6 times the derivative of x. Now this one's interesting. We haven't talked about this yet. Remember, the exponent there is a 1. So it's 6 times 1 to the x to the 1 minus 1, or x to the 0. Well, we know x to the 0 power is 1. So that's just a 1. And we have the derivative of 1. Well, the derivative of 1 is the derivative of a constant, which we also know to be 0. So we end up with 3 times 8x to the 7th, which is 24x to the 7th, minus 2 times 5x to the 4th, which is 10x to the 4th, plus 6 times 1, which is plus 6, plus 0, we don't need to write on there, and we have successfully found the derivative. Okay, now that was a lot, and you're going to try some homework problems where you're finding derivatives using all of these rules. Okay, so I want you to work for the remainder of class on these, and I want you to try some over the weekend. Make an attempt at all the problems. When we come back on Tuesday, I'll be here, and we will talk about those and then finish out a couple of other things in this section. Okay, so the assignment is on page 196. It is 1 through 24 all. Okay, so 24 problems. All right, have a good long weekend. I will see you all on Tuesday. Bye.